nucleus. The L quantum number is 0. Representation of orbitals and many electron atoms. So first off, we have our s orbitals. These are circles, they're spherically symmetric, and they are centered around the nucleus. The L quantum number is 0, and that just refers to the shape, so like the S, P, D, or F. So the way you measure electron density is through the radial probability function. So you can see that the n number on an s orbital is going to be the number of peaks that you see on the graph. So like for like 3s, there'd be 3 peaks. For 2s, there'd be 2, and for 1s, there'd be 1. The number of nodes, which is just like the dips in the graph, is going to be equal to n minus 1. So for 3s, it would be 2 nodes, and for 1s, there'd be 0, and for 2s, there'd be 1. So, and then obviously as n increases, the electron density becomes more spread out, and there is a greater probability of finding the electron farther from the nucleus. Next up, we have p orbitals. The L quantum number is equal to 1. The m quantum number can be equal to -1, 0, or 1, which just kind of refers to how it's laying out. They look like a dumbbell shape with 2 lobes, and there are 3 different types of orbitals that you can have in the p subshell. So you have pz, which is when it's like this, px, which is when it's like that, and py, which is when it's like this. The last 2 orbitals are the d and f orbitals. We know way more about d orbitals than we know about f orbitals, but the d subshell can hold 5 different orbitals. The L quantum number is 2. There are 4 lobes on a d orbital, and they can be located in the xy, xz, and yz regions, which is just like in between, like for xy, that'd be in between the x and y axis, and so forth. And then you also have dx squared minus y squared, which just means it's going to be along your axes. And then you also have dz squared. The f orbit subshell, has 7 orbitals, and we do not know enough about the shape of it. Is too complex, so we do not have to learn that. And now we are on to 6.7, many electron atoms. So the one atom that we use a lot to compare and to figure out stuff out about how atoms work is hydrogen. So the 3s, 3d, 3p orbitals in hydrogen all have the same amount of energy because they don't deal with electron-electron repulsion. So in pretty much all other atoms or elements, the 3s, 3d, and 3p will provide different amounts of energy because they do deal with electron-electron repulsion, which is just the multiple electrons in these shells reacting or existing near each other. In a many electron atom, for a given value of n, the energy of an orbital increases with the value of L. So that means that the 3p orbitals, or the 3d orbital, is going to have the most energy. The 3p orbital will have the second amount of energy, and the 3s will have the least amount, if you use these ones right here for atoms other than hydrogen. And then orbitals in any subshell are degenerate, which means that they have the same energy. So all the orbitals in this 3p subshell will have the same amount of energy. The electron spin was discovered by George Uhlenbeck and Samuel Goldschmidt. It just means an electron is spinning on its axis. This also came to be how they found the next quantum number. Hello, this is part 2. And where we left off is ms is the quantum spin number. Yeah. We determined this after we found out electrons do spin on their axes. There are 3 values that are used to note the different ways an electron can spin: -1/2, 0, and 1/2. The spin of an electron creates a magnetic field. And then the Pauli exclusion principle states no 2 electrons can have the same set of quantum numbers, which kind of relates to what was previously known as the Pauli exclusion principle, which is that 2 electrons need opposite spins in order to share an orbital, and that is because they cannot have the same set of quantum numbers. And if they had the same spin, then they would have the exact same set of quantum numbers, because they would already be in the same, they would have the same n value, and they would have the same value for being in the same subshell together. Alright, and then here is kind of with the problems listed for the book for 6.6 and 6.7, here is the average 6.6 to 6.7 problem. So find the quantum numbers n and l of 3p, 5d, and 6f. And I'll give you some time to pause it, is what I was doing. Okay, so for 3p, the n value is going to be the first number, the quantum number. And then the L is going to be the number that corresponds with the P subshell. That is 3 and 1, because remember that the S subshell starts at 0. For 5D, it's going to be the same thing, so 5, and then D, which is going to be 2. And then for 6F, it is going to be a 6, and then a 3. And that is the highest the L value goes. It goes from 0 to 3. So not too difficult. Thank you. Oh, I have to pause it. I have to